Can I continue, please?
Yes, yes, you can.
Yeah. مساء الخير. Good evening and dober вечер for everybody. My name is Kazim Al-Janabi. Professor of Computer Science, and I am the Dean of Faculty of Computer Science and Mathematics at University of Kufa. I am talking to you on the behalf of our university president, Professor Yasser Al-Mansouri. First of all, thank you his best wishes, and we hope that this workshop will be successful. Our university got the name of U of Kufa from Holy City Kufa, an ancient city located to the south of Iraq, capital Baghdad, about 140 kilometers. The city contains many ancient buildings, shrines, and mosques, such as Kufa Mosque, Al-Sahla Mosque, Maytham al-Tammar Mosque, and Dar al-Imam. U of Kufa was established during 1987 with 3 faculties only, and now the university contains 21 faculties in different specializations, including medicine, engineering, science, art, law, economics, agriculture, political science, and many others. More than 200 faculty staff and more than 30,000 undergraduate students and about 3,000 graduate students in higher diploma, MSc, and PhD degrees. The university also contains many research centers. About our Faculty of Computer Science and Mathematics, it was established during 2008 with 2 departments only, Computer Science and Mathematics. More than 600 students are studying at the moment, and more than 100 PhD, master, and higher diploma students are studying at the faculty. The quality assurance, program accreditation, and world university ranking are at the higher priority of our university strategic planning. Finally, I would like to thank all the workshop invited speakers, participants, organizing committee, scientific committees, and all who make this workshop possible. Thank you very much, and have a nice time.
So now we have, thank you, sir. Now we have now we have presentation of Professor Ilya Spitkovsky on the peculiarities of Toeplitz operators with almost periodic matrix samples. Please, Professor, your word.
Please, Dr. Ali, would you please introduce some of the people participating in the workshop?
Now we will have the
participating in the workshop.
Now we will start the presentation.
Yeah, okay. Yeah, let us start, please.
Given this is not an option under the circumstances, and we'll see how it will go. So here is the screen. First, some preliminary statements which hopefully will help to understand the place of the question I would like to pose towards the end. I hope I'm sharing the screen now. Tell me if it's not the case.
Yes, we see.
Okay, so let me start with a definition of a classical definition of the Toeplitz operator acting, say, on Hardy spaces on the unit circle. That's for simplicity. So A is a function from L infinity defined on the unit circle. There are Hardy spaces HP plus and HP minus inside and outside of the unit circle, and the respective projection of LP onto the space of Hardy functions is denoted by P plus. So this is what Toeplitz operator does. for any function f from the domain, first it multiplies this function by a, this symbol. As a result of this multiplication, most likely we're out of the space. And then the projection onto HP plus is used to press it back inside. And thus it is an operator acting from HP plus to HP plus. And the natural questions, well, there are many applications which I will not go into because of the time constraints, but main questions which we will be concerned with are: when is this operator Fredholm, when it is invertible, things like that. Some classical results, these going back to Simonenko.
Welcome and thank you for choosing free conference call. You're helping people around.
Great. So for this operator to be Fredholm, it's necessary that the function may be invertible in L infinity. Necessary may be sufficient, maybe not, depends on the class. But the criterion, necessary and sufficient condition, is given by theorem 2. And it says that the operator is Fredholm if and only if the function a, the symbol, is factorable. And what this factorability means is that the function is representable as the product of three factors, one of them a plus being analytic and invertible inside, a minus analytic and invertible outside, and in the middle there is a multiple d of t equal t to the kappa, t being the variable, and kappa here is an integer, and this integer is called the index of factorization in this case. And moreover, the index of the operator, of the Toeplitz operator in this case, is this kappa. Well, honestly, it is minus kappa, but it's a question of notation. This is a very nice theorem because it is a necessary and sufficient condition, but unfortunately, just restatement of one thing unknown in terms of another thing also not very explicitly verifiable, because when is the function factorable is a completely different story, and therefore some criteria verifiable in case of additional conditions imposed on the functions are of interest. And as such, for example, the following results are available. Say the function is continuous, then factorability is the same thing as invertibility, and moreover the index of the operator and the index of factorization in this case is simply the winding number of A, and as you can see there is no dependence on P. So this either holds for all P between 1 and infinity or for neither. Slightly more general setting, piecewise continuous, then the criterion is still available, though it's not as simple, and the answer depends on P now, and the invertibility is still, of course, necessary, but is not sufficient anymore. And the criterion sounds as follows. For factorability, it's necessary and sufficient that, number one, you have invertibility, which is always necessary, but there is number two, that is, for all the points where A is discontinuous, you take the ratio of its one-sided limits, which exist because that's how the class of piecewise continuous functions is defined. So you take this ratio, you take the argument of this ratio, and this argument has to be different from this magic number in the right, 2 pi over P. And this is how we depend on P now. And there is a formula for the index, which now also depends on P. It's very nice and beautiful, but there is no time for that because the talk is about something actually different. So where do we go from here? From here, we can go in two directions. And one direction is moving slightly into different classes of functions. Instead of continuous, let us talk about almost periodic, and I will give the definition in a minute. And in place of piecewise continuous, naturally will come into play the so-called semi-almost periodic functions, which I will probably not touch anymore in this talk. I will just say that semi-almost periodic is to almost periodic as piecewise continuous to continuous, and if we understand almost periodic case sufficiently well, passing to semi-almost periodic is not a problem. Okay, so here is the definition. The class of almost periodic functions is the smallest algebra generated by all simplest periodic actually functions, E lambda, which are defined by this formula. E lambda of x is e to the power I lambda x. And when I say the smallest algebra, well, you take the algebra in the algebraic sense, that is just linear combinations of such functions, which are called almost periodic polynomials. And then you close it, and you can close it in at least two different ways. You can close it in L infinity, and that is what the algebra of Bohr almost periodic functions is. And you can close it with respect to the stronger norm, this one, and that is APW. Whether AP or APW, there is a series corresponding in some sense to this almost periodic function. And the case of APW is exactly when the series is absolutely converged. And for such functions, which by the way are now on the real line, not on the circle, but this is a technical issue, not very important. Surprisingly or not, there is a statement very similar to that for the continuous case. That is, well, there are some changes, but very natural. Namely, the function is factorable if and only if it is invertible. The factorization notion has to be modified somewhat. Namely, the middle term is now not t to the kappa, it is e sub lambda, the simplest almost periodic function. The value lambda has now a name, it's not the index, it is the mean motion, which exists due to the so-called, well, one of Bohr theorems. And the Toeplitz operator, well, it cannot be Fredholm without being invertible, that's a change. But to be invertible, what it takes is that this f is factorable with lambda equal to 0. So the behavior is more or less like for continuous functions. And APW, by the way, behaves exactly as the Wiener algebra of continuous functions. Algebra of functions on the unit circle with absolute conversion Fourier series. And from here, the respective result for semi-almost periodic functions, which I will not go into, can be derived. It's a technicality. So this is one direction. Another direction which we can take is from scalar to matrix case. And here, if we stay within the class of continuous or piecewise continuous functions, nothing really difficult happens. Namely, I'm back on page 1, theorem 1 still holds. The operator is Fredholm implies that A inverse is invertible. It is still true that the operator is Fredholm if and only if A is factorable. The notion of factorization has to be modified, but in a very natural way. Namely, instead of this d of t, we now have to deal with a matrix. D of t will have to be diagonal, but the diagonal entries are t to the power kappa 1, up to t to the power kappa n, where kappa j are integers, and this factorization does exist if and only if the matrix function is invertible. Kappa j are called partial indices, and the operator is invertible if and only if partial indices are all equal to 0. And a similar statement to the one for continuous matrix functions. The change is very natural, factorable if and only if invertible. The index is naturally the winding number not of A, because there is no such thing, but the winding number of the determinant of A. And well, there are some peculiarities related to the fact that partial indices, as they are called, are not stable anymore, and the factorization cannot be found explicitly, as it was the case for the scalar functions, but that's all manageable. And for piecewise continuous, also some obvious changes are in order. Factorability is equivalent to invertibility plus something else, and this something else is also a condition on the arguments. Arguments are now not of the ratio of the two limit values, because, well, they are matrices now. So instead of taking the ratio, you should multiply one by the inverse of the other. And still there is no such thing as the argument of the matrix as far as I know, but matrices have eigenvalues and eigenvalues have arguments. And now the condition is completely set. The bottom line is that some very natural changes occur when we stay scalar but move from continuous to almost periodic. And some also natural changes occur if we stay continuous but move to matrix case as opposed to scalar case. And therefore, it was natural to expect that if we combine the two, that the result will also look more or less the same way. That is, and that was the expectation, that if we take a matrix function which is almost periodic, or to stay simpler in APW, then it will be factorable in a natural way. And here is the natural way. G should be the product of three multiples, G plus, D, and G minus. G plus analytic invertible in the upper half plane, G minus analytic invertible in the lower half plane, D also diagonal, because that's how it was for continuous matrix functions. And the diagonal entries now are probably like this, E lambda 1 up to E lambda n, where lambda j are real numbers which are natural to call almost periodic partial indices. So once again, the expectation is that invertible matrix functions are factorable, and the respective Toeplitz operator is invertible if and only if G is factorable, and the partial indices are all equal to 0. Well, that was, as I said, an expectation, and the reality is as follows. The second part is true. This. It is indeed true that the Toeplitz operator with almost periodic matrix symbol is invertible if and only if G admits what we call almost periodic factorization, and the partial indices of this factorization are equal to 0. So if the upper part were true as well, a natural approach would be as follows. Take an invertible almost periodic matrix function, factorize it. If partial indices are zeros, the Toeplitz operator is invertible, and if there are non-zeros, it's not invertible, but also has some nice properties which can be easily described. Well, the main message of my presentation here is that this is not the case. This is not a true statement. It is true, but not very exciting, that factorability implies invertibility. This is true, but the other way, it is not true. And moreover, it fails to be true even for 2 by 2 matrices. So already for 2 by 2, this is an issue. And the criterion is still unknown. So if I had no more time, I would have stopped here and have already considered my mission accomplished.
You have time. You have about 10 minutes more.
Great, and I hoped so. And in this remaining 10 minutes or so, I want to describe at least briefly what is known and, well, what is interesting about it. Well, there is one result which carries over from continuous case to almost periodic. This result involves the so-called numerical range, and the statement persists. Do I want to spend time on it? Probably not. So if there will be a question, I'll answer this question, but let me skip that. And let me tell you which matrices are already of interest. I already mentioned that for 2 by 2, the statement is not true. But even more than that, if we take a 2 by 2 triangular matrix with the simplest diagonal entries possible, E lambda and E minus lambda on the diagonal, 0 in one of the off-diagonal positions, and an off-diagonal entry somewhere. And moreover, if this f is just an almost periodic polynomial, so finitely many terms, already the criterion is not known. And let me mention that this is something which is important in applications, because the Toeplitz operator with symbol of this kind is closely related to convolution type equations on finite intervals, with lambda being exactly the length of this finite interval. And it is also related to some dynamic systems, but that I probably don't have time to go into. So let me tell you several things about this particular situation. As it happens, everything, not surprisingly, everything depends on the so-called Beaufort-Fourier spectrum of f, which is simply the set of coefficients different from 0 in the representation of f in the form Cj E lambda j. I'm sorry, it's not the coefficients, it's the exponents. The exponents for which Cj are different from 0. And as it happens, only the exponents between, only the exponents between minus lambda and lambda are of importance. So here are several situations. Case 1, which we call commensurable, is the case when the exponents all lie on some grid. The distances between them are commensurable. Then nothing unusual happens and the factorization exists and can be found explicitly for such matrices, so factorable. And this in particular covers the case of binomials. Why is it covers the case of binomials? Because if there are only 2 exponents, they definitely lie on the grid. The grid, well, the step of this grid is the distance between the 2 points. So if there are only 2 terms at most in f, nothing extraordinary happens. Case 2, the so-called big gap case. This is the case when there is a big gap, not surprisingly. That is, there are some exponents to the left, there are some exponents to the right, no order, no pattern is required, but there is something free, some free space in between. Let's say the gap of size D. So what makes it big? Big means this. The distance is at least lambda. And then again we're factorable, and moreover, the partial indices, I can tell you right away without knowing anything else, they are plus minus d minus lambda. And therefore the Toeplitz operator respective is invertible if and only if the size of the gap is exactly lambda. More than lambda, not factorable, but the operator is not invertible. And this covers what is called one-sided cases. What are one-sided cases? When all the exponents are, let's say, non-positive, or all the exponents are non-negative. Well, I drew them in the opposite order. But this, well, I hope you agree that this is a big gap case because these are your big gaps. This is the big gap here, this is the big gap there, and invertibility will take place in this setting if and only if 0 is actually in the spectrum. That is when there is a constant term. And finally, as far as this presentation is concerned, case 3, the simplest case which is not covered. So what is the simplest case? Well, we need at least 3 terms because 2 terms are covered. We need at least one positive, at least one negative. Is everything okay?
Yes, yes. No problem. It's okay. No problem.
All right. So as I was saying, we need at least one positive point in the spectrum. Let's call it alpha. We need at least one negative. Let's call it minus nu. The third one in the middle, let's make it 0. This is an additional restriction, but not that bad. Also, alpha over nu should be irrational, because if it is rational, this is a commensurable case which had been covered already. And one additional condition which we will impose, and this is indeed restriction, is that we want alpha plus nu to equal exactly lambda. So this distance is lambda. And what happens then? Then there is a criterion. In terms of the coefficients, for the first time, the coefficients are important. Let's say they are C minus 1, C0, C1. Then the condition looks as follows. You take C minus 1 by absolute value to the power alpha, absolute value C1 by to the power nu, and on the other side, absolute value C0 to the power lambda. And these two quantities have to be different. This is necessary and sufficient for J to be factorable. And when it is factorable, the partial indices are actually equal to 0. If factorable, this respective Toeplitz operator is invertible. And even if we still have only 3 exponents, but this condition being violated, there is no answer. There is no criterion no factorability criterion, and the question remains open. Well, this is not the up-to-date picture. There are many more particular cases which have been settled, but this did not make the situation any less mysterious, because each particular case was tackled in its specific manner, and for every situation there is an explanation why things are the way they are, but there is no bird view at that, no general picture, and we still don't know.
About 2 minutes.
Okay,
It's about 3
I'll not
2
go
minutes.
over the limit. So what I want to say in addition is that this particular case, case 3 from those I have discussed, is actually indeed related to some dynamical issues. Namely, as I already mentioned, the convolution type equation on finite interval is closely related to almost periodic factorization of matrices of this type. And in this particular case, this convolution type equation is actually a weighted shift of the circle. And the invertibility criteria for this weighted shift are reflected in this criterion for factorability of the matrix. Maybe there are more involved relations between the two topics which would allow more progress here, and this is my main reason why I decided to speak about this at this particular conference. So I will stop here, and I will be happy to answer questions to the extent possible with this mode of communication. And thank you very much once again for giving me an opportunity to speak here.
Thank you very much for your talk, and actually following the microphones didn't allow me to have a questions now. But my question,
in case of rational,
I mean, in case of now we have irrational number. So
in case of rational number, the factorization will exist because it is covered by case 1. The partial indices are not necessarily 0, but there are formulas for them. And so they actually depend on the coefficients then, and there are formulas.
Okay.
And there is a criterion for these, for the partial indices to be equal to 0. There are criteria even in a general commensurable case, not necessarily when there are only 3 exponents.
Okay, thank you. So I will turn on the microphones, and I hope if someone have a question to ask, or you can turn on your video and raise your hand and ask a question. So anyway, I don't see any question.
Okay, I guess I can stop sharing the screen now.
What, Professor?
Hello.
Yes.
I am Dr. Sadek Ali from India.
Hello, Sadek. Do you have a question? What is your question, please?
Hello, sir. Yes, my question is, at the inception, you have defined a E lambda is equal to e raised to I lambda x.
Yes.
And among these two parameters, lambda and x, one of the parameter belongs to the set of integers.
No. Lambda can be any, well, I can't find that page, but many other page as well. So E sub lambda, it's simply an abbreviation for e to the power I lambda x. X is our variable, which is real, and lambda is a parameter which is also real. It doesn't have to be an integer.
So what I feel, this e raised to I lambda x is what I'm thinking. It is like a kernel of Fourier transform.
Yeah, there is a relation, yes.
So can we use a Fourier transform to design such a dynamical systems or analyze?
Well, the thing is that this is not one lambda. We will have a function there which is the sum Cj e lambda j, and there are many lambda j's, maybe even infinitely many, and that represents a difficulty.
Okay.
So,
Okay, thank you.
I was always Professor Kaftanenko has the questions, but I don't know now if he has or not. So,
All participants are muted and they can unmute themselves.
so I would like to. I don't see a question in.
I want to stop sharing the screen, but I can...
Yes.
Okay, I stopped sharing the screen.
I don't know. Please type your name to turn on the microphone if you have a question. Who want to ask? Please type your name in the chat to turn on the microphone for you. Because I can't turn on all the microphones, it will be something unbelievable. Dr. Muhammad, so Dr. Muhammad wants to ask.
Assalamu alaikum. Thank you for your presentation.
Yes, please.
My question, you have matrix 2 by 2. The diagonal of this matrix E lambda and E minus lambda. You define lambda greater than 0. And another place you define lambda belong to R. Why you put there lambda greater than to 0? We can put lambda less than 0, or in general lambda belong to R?
So I think the question is Professor Spitkovsky. Just a moment.
You hear me, Dr. Ali?
I hear you, but I'm not sure Professor Spitkovsky hear you.
I'm sorry. Somehow I got muted.
Oh, no problem.
Yes, I can hear you.
So,
well, maybe I'll try to explain without sharing the screen. You remember when I was considering these 2 by 2 matrices, I mentioned that only the exponents between minus lambda and lambda matter. So if lambda is negative, this becomes the empty set. And therefore, when lambda is negative, actually F can be dropped out. And the matrix behaves the same way as if it were diagonal, and therefore it's factorable. So this is allowed, but this is not an interesting case.
Okay, thank you.
Thank you.
No problem.
So anyone wants to ask, turn on your microphone and ask, please. So according to the connection, we will wait just 1 minute and then so I think.
Well, let me tell you that if it were a normal conference, I would be very happy to meet the participants in person, and that would be very helpful and beneficial. Unfortunately, this is not an option nowadays. But if you think of any questions that you would like to discuss, you probably have my email address by now, and you're welcome.
Okay, so let's thank the...
And I remember seeing,
Yes, please.
yeah, I remember briefly seeing Professor Antonievich there. I'm not sure if he's still there, but
He is here, Anatoly Borisovich, если вы слышите нас.
glad to see him at least in this.
Yeah.
Да. Нет,
А мы поговорим
отдельно, да.
индивидуально.
Хорошо, тогда. Okay, so let's thank the speaker again. So thank you very much, Professor Spitkovsky, for sharing your valuable time and make this nice experiment happen. And it's very exciting to have you here and we see you again. And actually, a lot of friends now I see Professor Kaftanenko. I had not seen him for a long time. Anatol Borisovich, my PhD supervisor, also all my friends here from different countries. Thank you for coming and make this event happen. Thank you, and see you again tomorrow at the same time. Thank you very much.
Thank you. Thank you.
See you tomorrow. Thank you.
Thank you.